My last project is about creating waveforms. This is a project which I cannot really demonstrate because it's actually part of my ADM scope. So I have no setup where I can really show how the generated waveform looks like. I could have used the ADM scope, but I actually did not. Generating waveforms needs, for the first part, and digital to analog converter, which outputs data through a pump to a pin. This is the simple part. The next part we need is a DMA component which transfers the proper values for the waveform from memory to the VDAC, and this DMA is triggered by a timer which handles creating the right frequency for the desired output frequency. So we run this timer from the bus clock, which is 38 megahertz. Then we program this timer with the right division value or the right divider value to trigger the DMA in always the same frequency, which then writes the output value to the VDAC, which creates the desired waveform. We can influence the frequency of the timer via external inputs. There are two inputs which can be used for voltage control, meaning when I'm adding a frequency, a voltage above half the analog supply voltage, which is used as the reference voltage, to one of these pins, it increases the output frequency. If the voltage is lower than the reference frequency, the output frequency is reduced. And same can be done with a potentiometer, which is the one already placed on the development kit. The last component we have here is a synchronization input, which can be used to synchronize the waveform generation to an external signal. When this comparator detects an input signal which is above the reference voltage, also half the analog voltage here, it creates a pulse, and if this pulse is decided to be longer than 10 microseconds, then we trigger a synchronization, which in turn just resets the DMA, so waveform generation starts again. From a program perspective, it looks rather simple. We have two waveform tables here, one for sine wave, one for ramp wave, meaning a triangle. We have all the constants for the DMA. The program itself starts with setting up all the components. Then we have the main program, which handles the button presses on the capacitive display. On the capacitive buttons, you can select the waveforms, choose between sine and ramp. If you do this, we just select the waveform and change the DMA to use the proper table from the RAM. Also, we can select the frequency with the CapSense buttons. You can change the frequency itself with plus and minus, or with using the capacitive slider. You can use a potentiometer, the external VCO potentiometer, or you can add all of them together. And if the button press is registered, we just change the frequency, and in the end calculate everything together, and in the end just set the frequency to the DMA. Frequency calculation itself is just done because we know the reference frequency we know how large our table is and we can calculate the divider from that. Here you can also see the big drawback of triggering the DMA by a frequency divider, because for higher frequencies the resolution of which frequencies we can choose is rather poor, with bus clock of 38 megahertz and 32 steps in our waveform table. We get, even with a divider of 1, meaning we reach this through, we get a frequency of a little bit about 1 megahertz. If we increase this divider to 2, we halve this frequency, so there is no way to create, for example, 900 kilohertz, because you just cannot do this with that. For that, I have another solution, which unfortunately is in another project. The other scenario, or the other way for creating waveforms, uses what is known as numerically controlled oscillator. It, in its core, consists of what is called a phase accumulator, which is nothing more than a counter, which is not working as a normal frequency divider, but it just adds predefined step value to its counter and uses part of the current counting result as the lookup pointer into the waveform table. This phase accumulator has been developed by the PSoC Sensei blog, which can be found on the Cypress website. It gets fed by a 12 megahertz clock, which in the end leads to an update frequency of 1 megahertz, which is also used as clock for the DMA. This is because the phase accumulator internally needs 12 input clocks to create the next value for the output value. So we have this phase accumulator running freely, and then we have our clock DMA, which just triggers the DMA, which retrieves the next value from the phase accumulator and creates from that the lookup value, which gets then written to the output digital analog converter, which just writes the output value. From a program perspective, what looks different here is we have a much larger waveform table, because when using the phase accumulator, you can actually skip values in here. So even when this is 1000 samples large, you can choose for higher frequency to skip every 9 out of 10 samples, meaning you would choose every 100 of them and create different frequency from that. The program itself is also rather simple, because it just initializes the DMA, which gets not changed here, because we always generate sign tables. The first 2 steps of the DMA retrieve the current lookup pointer values from the phase accumulator, and the third step writes this to the digital to analog converter. After that, we initialize the phase accumulator with an increment of 400. We create actually a frequency of about 2.5 kilohertz.